Okay, let's talk about this. So I don't have any preparation for this, so it's totally improvised and I have no idea how far we can go. But the idea today is to talk about this procedure generated planet inside Shadertoy. So I think this can be an introduction to Shadertoy programming. Shadertoy is a very constrained programming environment. Inside Shadertoy, you can only do one thing, which is fragment shader. And that is exactly what I am doing. For fragment shaders, each each of these little programs are run on one fragment, or we can also understand it as just a pixel on the screen. And the thing is, we don't have, like in normal CPU programming, we have this kind of just one thread and we create geometry and then we display the geometry. Inside this shader, we cannot do that because we only have have this program run on each pixels. So what we do instead is trying to find a way to say if this pixel is part of that geometry. And then we can just try to draw. And to have that, we introduce the concept of sign distance function, which I will show you here. This is the new Shadertoy playground. If we just have a circle, sign distance function, and we say if we have a point on the screen, and in shaders everything is in shader programming, we have those kind of vector 3, vector 2, vector 3, and vector 4 to deal with. Those types are quite nice. But also notice we don't have colors or points. Everything is vectors. So whether we have color, point, or direction, we always have this vector tab. And let's see. So what do we have here? We say is at this point, we need to know whether this point is inside the circle or not. And the circle is defined by a center and a radius. So, but for sign distance function, we not only know whether, but we actually also returns a float instead of just a number. We will see how this can be useful later. And to calculate that, what we will do is so what we do is the square root of the point minus the center square. So this is basically we will trying to get the distance from our point to the center of the sphere. And then we minus radius. Afterward, if this number is positive, then we get something outside of the sphere. If this number is negative, we get something inside the sphere. And then we can just say if, for example, if this number is negative, we display red, and otherwise we display black. And we can do that with our UV coordinates, which is 0 to 1 and 0 to 1, I think. Any questions so far? And we have a circle in the center. But since we are using the UV coordinates, we are actually scaling to perform some kind of scaling because it's 0 to 1 in width and 0 to 1 in height. We can fix that by use this frag coordinate. But if we use frag coordinate, we also need to change those. Otherwise, we cannot see anything because our sphere is too small. Okay, here it's like 500. 500 is probably too large. Yeah. So you may ask what is the advantage of sign distance function? Like obviously in Shadertoy we can only do that, but why this thing is useful outside of Shadertoy context? For one reason, there are just shapes really hard to describe analytically. So the only way to describe is with this kind of implicit functions. But there are other advantage of this, which I will show you next. So we create this thing SDF, and the thing SDF will be two circle SDF.
Lesley, John has a question in chat.
Yeah, so the dot product is we just get a square, just get the square magnitude of the line to centers, and then we do a square root immediately afterward to get the distance, basically. So I think, yeah. Oh, what does the subtraction of the radius do? So subtraction of radius is Otherwise, we have a distance from center. By subtracting with radius, we get this sign distance function where the positive sign means it is outside of this sphere. Negative sign means it is inside this sphere. And yeah, that's why we do this subtraction. I forgot it's min or max. Let's just try it. So instead of previous circle SDF, we have this scene SDF that is the composition of the two circles. Okay, I got it wrong. Yeah. So min is union and max is intersection of the two shapes, basically. You can see with sign distance function, it is really easy to compose those kind of shapes. However, when we do this kind of max and min trick, one thing changed is that from some arbitrary point towards our surface of this shape, the distance is probably no longer the exactly distance to the shape, but the distance will guarantee to be some number that is smaller than the distance to the shape. That is important when we talk about 3D. So this is 2D sine distance field. We can do crazy stuff with it, like this is something we did in the graphics club before. It's pretty stupid, but you can just see how this kind of thing can go. But 2D is not what we will talk about today. It's just an introduction to sine distance function. What we will talk about today is 3D. For 3D, it's just like 2D. We have 3D points and the center becomes 3D. For the circle, this doesn't even change. Of course, for the more complicated volumes, then we have more complicated sine distance functions for them. And for the thing, let's just get rid of the second circle and just use the first one. We can see the center is at origin. Radius 50 is fine. And we need a 3D point. But now the problem is how to get this 3D point, because drawing 2D stuff into a 2D surface is easy. Drawing 3D stuff onto a 2D surface, we need some kind of projection. So first we need to generate some rays for each pixel to reflect the projection. And in this case, I will use the perspective projection camera, which means it's like how normal eyes view stuff, where if we have a camera here, then it will see as this. So this object will be shown as really big, and this will be shown as smaller. There are alternative way to do that. It's called orthogonal camera, which is a camera like this. And then shape as this shape and this shape will be seen as the same. So we will have projection camera, and I will just copy the code from here. So first we need to have array. And we need to get the point onto that array. This is just the array is a function. The array is a function of origin plus the whatever the argument we pass in times the direction. So we need to get a point on that array based on the parameter t we passed in. And we need another function to generate the array, but where it is. So now with this code, we can generate array. We need an I direction, which I cannot set it at origin because we already set the sphere at origin. What's the setup in here? Yeah, that looks nice. The next step is we have array, and when will it to intersect with this sine distance function, which is an implicit surface defined by this function. Well, with that we need ray tracing, but not normal kind of ray tracing, because normally for ray tracing we can get an analytic solution from the surface and the sine distance function. But since sine distance function is arbitrary function, we cannot guarantee to get an analytic solution. So what we will do instead is this process called sphere tracing, where if we have a surface like this, for each point above the surface, there is some distance toward the surface. So let's say we have an array like this. Our distance is this range. So the next time we will just trace from this point toward the distance, toward the direction of the array with the distance we have before, with the distance which is this. Notice we don't have an intersection yet. So what we need to do is just repeat this process to do it again with that distance, and then do it again until we have a point that is, until either we have too many iterations, then we just quit, or we have a point that is really close to the surface, then which means we have a very small number. In that case, we will say we intersect with the surface. If you remember Newton's method from calculus 1, then you will realize this is really close to Newton's method. Just like ray tracing is finding analytic solutions, just like you solve a differential equation directly, and then this sphere tracing is like numerical integral of that sphere tracing of that differential equation. It's same kind of stuff, just analytic versus numerical. And this is the thing we must do for sine distance function. So how to implement that? We create this trace function. that should take the ray in. And then we just want to know whether it intersects with this thing or not. So first we need some t, which is starting point 0. And we do a for loop to mimic the numerical integral process. We will set 50 to the maximum iterations. And then we just say get the point, which is at and then get the point on that ray. Then we need to find the sign distance of that function of that point. Sorry. And then if our sign distance is less than some very small number, because of numerical reason we cannot use 0, then we say we hit the surface. Otherwise, we don't. And then the last thing we need to do in here is to increment the t. By the distance. So then we can trace the next step. We can do a little bit of optimization that is not the most important part of the algorithm. That if our t is too large, let's say 1,000, we just quit. That means we trace very far and we haven't found a point. Oh, is this sphere too large? Probably. Yeah. So we have a sphere. That's red. That's we can't even tell if this is a sphere or a circle because it's just red. But however, if we just add some dummy lighting, then it becomes clear it is a sphere. But first we need to get the normal of the surface point, where I will just copy the code here because I don't really understand how this normal is calculated. I used to, but not now anymore. This is the function that used to calculate the normal sign distance field. So there's a book called Graphics Index. I copied this particular code from there. So if you're interested, you can find the code there. And we don't need this. Normal of that point. now here, now here we can no longer do this, but instead we will say color is initially black. But if we find the array, we get colors is equal to the normal. Now the problem is we don't have this point. So, but this point is calculated in our trace function, so we can just make it output a point. And GISL is a very primitive language, so the only way to do this kind of stuff is use out parameters. We can do this. So we will output a point. And now we can see the normal vector. So the normal vector is just a unit vector that is orthogonal to the surface. Notice apps where you usually say it's usually very blue-ish, but in this normal, we can see some part of it is black, some green, some part of it is purple, because, and the center part is blue because we are doing like word space normal, not in the normal mapping, where normal mapping is like we flatten this sphere to a surface, and then the color of normal will be really close to whatever is in the center. In this case, blue is 0, 0, 1 because which means the vector is directly point upward. Wait, there are two other chats. So Laura, can you monitor the chats? Just tell me if there's any more questions. So the min is negative when it is inside either circle, and if the max is negative, it is inside both circles. Yeah. Yeah, exactly. So we have a sphere. We can even have really simple lighting for that by using the dot product of the normal and the ray direction. As a light intensity. This is called Lambertian lighting. It's the simplest way to have some quick lighting on the screen. And no, this is absolutely not right. Okay, add some diffuse color. Oh, because the normal is backward, we need the negative of we need to negate the dot product. Yeah, so this looks right. So if we have a camera, we have a light source exactly at the camera, and then we apply this dot product formula. we can get this kind of Lambertian shading, and we can do way more complicated stuff like plane form or even quick torrents or more advanced BLDF stuff. So, but the point is we can apply lighting to this thing. And then the next step is, what if we add some disturbance to the thing? Like we will just do something really dumb because I don't have time to talk about noise, I think, but you will see my point. This is too large. And this is too small. It just doesn't look chaotic enough. Yeah, so like with this kind of simple mass, we can get really weird shapes with signed distance field. And that is the point of signed distance field, is this kind of shape is just impossible to describe with analytic solutions. So we need signed distance field to describe this kind of shapes. Now let's go back to the procedural planet. For the remaining parts, I will not live code. We just walk through what I did. So the first thing is, in here I use this sine function, sine cosine function. This is a classic trick to introduce some kind of wave-like stuff into the shader. And in here, instead, I use a noise function. Where's my noise function? Yeah, I have this noise function, and then I add some kind of like level of details of this noise by use this fractal Brownian motion. So if you want to learn more about this and the noise, there's this book called The Book of Shaders that have some good introduction stuff of the noise and fractal Brownian motions. And with that, I can have this terrain. And also trace separately of water. So the word water is just really dumb sphere with some sine cosine disturbance. It's not as complicated as it can be. Like there are people in Shadertoy doing really advanced water stuff. But I just didn't. Yeah, you can do really advanced stuff with water. And then for the lighting, I applied this plane foam shading, which is a little bit more complex than our Lambertian shading. So instead of one line of code, it's like 10 plus lines, but it's still pretty simple. And the result looks quite decent. Another thing I do is I calculate the elevation by saying how much the distance it is from the center of the sphere, which is the elevation of that point. And then I assign them to certain values, like if the elevation is high enough, it becomes snow. If it is low enough, then it's vegetarian. And if it's still lower, then it becomes water. What else? Yeah, I think that's everything I want to talk about this. I tried to implement refraction, but it is broken. It looks totally wrong. And from the dates, you can see I just stopped working on this because I just tired of this. And yeah, that's it. Any questions?
That's pretty cool. You John's got a question.
Is the direction come from the camera? Yes. And does the loop give us a point, the first thing that ray hit in that direction? Yes, exactly. No. So remember how our algorithm work? This is not normal ray tracing. This is a numerical version of ray tracing. That's why we don't need to check for multiple objects. Let's say we have just a separate object here, and then we want to trace. What we will do is, let's say we have a ray like this, let's say. In here, the distance towards this sphere is like this, right? So we will probably trace to here. And the second step, we will probably trace to here. And then we say it's close to this. So we just return here. And we don't need to check for what is below. This algorithm is called sphere tracing, or more colloquially remarching. But remarching is kind of a like umbrella concept, and sphere tracing is a specific algorithm. Just like ray tracing is like even more of an umbrella concept. Yeah. If you want to read more, then there are a lot of information about this. Any other questions?
Can you go back to the code? So then are all of the objects already in the math for the one thing that you check in the loop? I forgot what the function was called.
Inside the loop, you mean like
in the one that you wrote.
this one, you mean?
Yeah. Are all of the objects inside of seeing SDF?
Yeah.
Okay.
Yeah, seeing SDF just contains this no longer circle because I put some random stuff there.
Thank you.
Yeah, I think it's probably a better idea to make circles up here. Cool. Yeah, I hope this can be an inspiration of Shadertoy. Just like with just really simple math, you can play a lot of cool stuff. Like what people can do with Shadertoy is crazy amount of stuff. even though I don't have that patience, so I just do some simple stuff like this.